Hi, so this is the second video on chapter 3. And we're going to discuss a few more details which we didn't have time to cover in the previous video. In the previous video, we talked about vectors and matrices as from a pragmatic point of view, sort of like what you can do with them, what are the operations. It's more like establishing vocabulary, your lengths, trace, determinant, what are the operations you can do on them. But we skipped over some important details, so that's what I want to do now, is go and make sure these things are said. Everything that should be said is said. Right. So this is, in fact, the concept of linearity, which actually even before chapter 3, it starts in the introduction. So this book kind of has two introductions. There's chapter 3 is an introduction, but there is also an introduction and beginning. So yada, 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 linear models predict the world. This is all like sales pitch for linear algebra, why you should learn it. But notice the first equation. So that should tell you that it's important. What is the first equation in the book? Is this equation, which is really the definition of a linear function. So let's just break it down a little, like look at the components. You have some sort of objects, I mean they're drawn in bold, could be numbers, could be vectors, we'll see all kinds of things. And when you combine them in this way, this is called a linear combination. So you take a coefficient, some constant a, times one of the objects, times x1, and another constant times b, and it's a sum of these. So this is called a linear combination. And what happens, here is some arbitrary function f, which we don't know what it is, but we're told it's linear. When you know something is linear, this is what it tells you, is that a linear combination, if you input ax1 plus bx2, the output will be a linear combination of the outputs, a times the output of x1 plus b times the output of x2. This may seem like a arbitrary thing, but it turns out it's really important. Like this structure is the key to, I mean, we have an entire book. Look at that. Computational, geometrical, linear transformations, all these concepts, you should look at these on your own. I don't have time to go over them. Somehow related to stem from this simple property. Basically, if you don't have linearity, function is nonlinear, it's really complicated. Like you can't, it will be difficult to study and difficult to parameterize, so linearity is something very special. All right, so let's switch over here to the computer world and show some examples of linear and nonlinear functions. See if we cannot see some common structure in there. This is the usual setup. I import SymPy, make everything print in LaTeX, define some symbols. We're not going to be plotting anything today, so we don't need that. So what is linearity? This is the Python syntax for defining a function called f. And this is some arbitrary, I mean, you can make it do plus sin of x, let's say. So this is an arbitrary function. F of 1 is what it looks like. F of 2 is this. What about f of 1 plus 2? All right, so this is the question we have today. Is inputting, and here the linear combination is kind of simple, it's just 1 plus 2. When we input f of 1 plus 2 into an arbitrary function f, like I don't care what it is, do I get the same thing as inputting the individual elements and then taking the sum of the outputs? So let's look. Let's just compare f of 1, this and this. So 3m, sin 3, oh, that's not right. Okay, so right off the bat. So you might say, no, the sin was, don't sin. Good advice in general. So this looks pretty linear, right? It's the equation of a line. You multiply the input by some constant m, and you add a constant. So that's what happens when the two inputs. This is for the combined input 3, right? Whoops, not the same. So 3m part is the same, but the b, each time you use the function f, it adds a constant b. And therefore, when you use it twice, you get twice the b. When you use it on the combination 1 plus 2, you get once the b. So not linear. Turns out, if you want a linear function, so the most general linear function that takes one input, so the input is just the real number x, has this form. So that's linearity. You know, it's proportionality, if you want to call it. When you input, the output is proportional to the input. If you input 5, the output will be 5x. If you input 1, if you put 2, you get that 2 times. M is like the slope, but let's think of it without adding too much geometry for the moment. Just m is some coefficient. So that's linear. You make the input twice bigger, the output gets twice bigger. Let's leave for the sum of the inputs is 3m, and that's equal to the sum of the outputs, 3. this function, I mean, let's you know, we have the equation. It's a definition, really. You say a function is linear if it satisfies this. So we can check this x and y here, arbitrary inputs. So this is verifying that f is linear. I had to do expand here. Details, because equality compares expressions exactly. So, all right. So that's an example of linearity. The lesson to learn is that linearity for single inputs, for single variable inputs, linearity is the same as proportionality. The input gets multiplied by a constant. If you have vector inputs, so here vec is now a two-dimensional vector. It has a x component and a y component, or a first component and a second component. And we want the function. So t is a function that takes a 2D vector and returns a 1D number. So the most general, so generalizing the notion of linear of proportionality when you have two inputs is you have two constants, two proportionality constants. So the first input, Python uses zero-based indexing, so this is really saying the first component of vec, even though it says 0, it's the first one, times some constant, and the second component of the input times another constant. So that's the most general function with two inputs and one output. Let's see what it does to u. If you input an arbitrary vector u1, u2, you get m1 times u1 and 2 times u2. This is a number here. Same thing if you do it to v, just the linear combination of the inputs. If you do it to the sum of f, u, and v, nothing that interesting happens. If you do t of u plus t of v, you should get the same thing. If you want to see this, so you see it's the same thing. Whatever you input, whether you input the sum of the two vectors or the individual, or you input them individually and take the sum of the outputs, you get the same expression. If you run it like this, it says yes, t of the sum is equal to t of the. In fact, here we define two arbitrary constant alpha and beta. So let's verify the most general formula. Alpha times u plus beta times v should be equal to alpha times and beta times v. Better be true. Fuck. Why is it not doing this? So okay, so this is just this is what we want to verify, right? That this is equal to this. Now, the way to do this in SymPy, because it's all kinds of expression, is to say simplify the subtraction of two expressions. If you want to check the two equations are equal, that's how you do it. You rewrite them as as an expression equal to 0, then you say simplify. So this expression is 0, so that means that this equals this. So otherwise, SymPy doesn't treat, I mean, depending on the way the expression is written, you want equality one. Equality is really like whatever is on the left is on the right. And this tells you, try to simplify the expression, not just compare them as they are. So yeah, t is linear. So that's the most general equation that takes two inputs and produces a single number as output. Notice the structure. You take the first coefficient of the input, the x component if you want to know, multiplied by constant, and same for the second, another constant. All right. Now this is telling us to go to page 116, and so it shall be. What happens on page 116 is we want to talk about linear transformations, or so known as vector functions. All right. So in high school math and calculus, we studied functions that take a real number as input and produce a real number as output. Linear algebra, we study a more general class which takes n-dimensional inputs and produces n-dimensional output. So you think of these as vector functions. It takes an n vector as input, produces n vector as output. And the set of linear transformation is the type of vector functions that obey the linearity property, which we just discussed. So taking the cue from the simple examples, the most general, so this is a function that takes a two-dimensional vector as input and it produces a two-dimensional vector as output. The most general way to do this would be to have some coefficients, right? Some arbitrary coefficients, and you take the input. The output has two dimensions, right? So the first dimension of the output is some linear combination.
It's 11 o'clock.
It's 11 o'clock of the first two inputs, of the zero dimension of the first input and the second input. And the second output is also some linear combination. And this is the way to return a vector. You say, right? So I'm claiming this is the most general linear combination. You can take a look at it. We can take a look at it. Yay. And we should probably run this because t is from the above. So you see, it produces a vector now. The top coefficient is this mix of the two inputs. T of v will be the same linear combination of the coefficients of v this time. T of u plus v is, yeah, not very surprising. But the point is, for a function to be linear, so a linear transformation has this structure where each of the output is some combination, some coefficients multiplying the inputs. That's sort of the X-ray version when you look inside what this does. Let's switch back to a more abstract way of thinking about this. And I say linear transformations are functions or vector functions. So you should be familiar with functions from high school. So you know, like, type of inputs the function has is called the domain, the output space, the range, the image, all these terminology that you know about functions from high school math will still apply to vector functions, linear transformations. And in fact, this will make learning about linear transformation very easy if you remember. So that's what I wanted to show here on page 116. So there's this is a function that takes a real number as input, produces a real number. What we'll study in this book is linear transformations that take n-dimensional inputs and produce m-dimensional outputs. I'll talk about that in a second. So the input here would be normally a number. Here the input is an n-dimensional vector. The output is a m-dimensional vector. Okay, so I mean, this could be the same, but in general could be different. Remember what happens when you compose functions. First, you apply f to x, and then whatever comes out, you apply g to the output. So you can do that with vectors, with vector functions too. There is a notion of an inverse transformation. Remember, when you say f of x equal to 0, these are called the zeros, the applications where f touches, f could be some arbitrary function. The points are called the roots where f touches the ground. So when talking about vector functions, linear transformations, these are going to be called the kernel of the linear transformation, or null space. So the image of f is the set of all possible outputs, and so there is these new concepts that you haven't seen before will turn out to be analogous to things you have seen before. So you want to look at that table when you're learning about linear transformations and see, they're not completely new things. I mean, we're just adding more dimensions. So if you think like, whoa, what just happened here? What's this arrows? It's the same stuff that happened in high school, but with more dimensions. So now the last thing I want to talk about. So here was you might think it's a new topic, linear transformations functions. But remember in the previous video, we talked about the definitions and talked a lot about matrices. So what's the link between vectors and matrices? Well, it turns out the matrix vector product is this link. When I say apply, for example, here, I say apply this linear transformation to this vector u, doing this manipulation. This structure here looks very much like a vector product. I mean, you want the output of this function is some linear combination of the inputs, and there's these coefficients that are named a particular way. So that's the crazy part, is that any linear transformation from n-dimensional inputs to m-dimensional outputs can be represented as a matrix vector product. I like to say implemented. So instead of doing this manually, you define a matrix which contains the coefficients, and then the output will be just the product of the matrix times the input vector. So this is what we see here. If you wanted to have the output y1, y2, y3, here is a 3-dimensional, here it's a 2-dimensional, to be the following linear combination of the inputs, you would put them in a matrix and say I'm doing matrix vector product. So that's I mean, kind of important. Let's look. I'm going to run this. So you see that this matrix, so here we had the general, like from first principles, putting coefficients and producing a vector output. And we get the same output when you put u, if you do the matrix vector product. So in fact, that's the whole point of matrix vector product, is defined because we want to be able to do linear transformations conveniently. So that's the story, the link between matrices and linear transformations. Right? I mean, when we were defining the matrix vector product, we could have invented some other operation. You say x times this time, right? We're calling it a product, but it looks nothing like the usual product in, when I say multiply two numbers, you just do this times this. Where here we said, we're going to take a linear combination of the columns of the matrix with x1, x2 as coefficients. So like this definition is weird. Well, it's kind of arbitrary, but turns out to be really useful. So every time you want to do a vector function, you can actually do it as can define a matrix and then just multiply the vector input times that matrix. So that's all there is to say about chapter 3. I hope this makes sense a little bit, and we continue with chapter 4 next time.